Okay, good morning everybody. So we only have 2 lectures left. So today we'll talk about system design. At the end of the lecture today, later on today, I'll put on the web a trial exam, and which you should try to do exactly like the real exam. In other words, in 2.5 hours without textbooks or anything. And you all have to bring in the trial exam on Tuesday. Okay? On Tuesday we'll go over the trial exam. You wouldn't have the grades, of course, yet, but we'll go over what you should have answered, just so you know what to do. And then and that's it. And Tuesday we'll do some summaries and some more system design, and that's it. Okay. Yes. Is this something we turn into after we go over it, or? No, you turn it into Tuesday morning. The exam will be released today. Today you have to go to after this. So I mean, is it submitted for a grade, or is it just for our own? No, it's a grade. It's 10% of the grade. I explained it before, so I'll explain it again. So today after lunch, if you enter on the Connect, the website Mac520, there will be a trial exam posted. Okay. Now you have to you have to do it as if it was a real exam, just for your own benefit, so you know how much you have to learn for the real exam. Okay. Then you bring it in on paper Tuesday, okay? And Tuesday I'll explain what you should have answered. It's not a difficult exam, but just we'll go over it so you know what's expected. And this will be graded, and the trial exam is 10% of your grade, which isn't much, but still, it's like an assignment. Basically, it's like an assignment, okay? And the rest of the time, today and Tuesday, we'll cover by talking about system design. Because we already covered in this course the sensors, we covered the interconnects, we covered the actuators. So now we should talk a little bit how you do system design, how you connect all these pieces together. Okay? Good. So the basic requirement of a servo system typically is if it gets a command, and it doesn't matter if it's a position command or a velocity command or any kind of command, it gets a command to do something, and the actuator has to follow this command. So if it was, in the simplest case, it's some kind of a position servo. You have a stepper motor with a lead screw, you have a DC motor which moves a robot arm, and this is a position command. And then you look at the response, and the response of the servo will look like this. It will start moving a little bit later, so there's always going to be a little bit of delay. So let's start with this corner. Why would there be a little bit of a delay? When you give a servo a command and you look at an output, like at a motor or a solenoid, so there's always a little bit of delay. Okay, so there's a few reasons for that delay. The first reason is electrical. If you're talking about electromechanical actuator, the electromechanical actuator, when you give it the command, say the current jumps, nothing happens because of something you all know, there's a time constant, okay? So just because you gave it a command, even before inertia, it takes a time constant, say L over R, until the current really is strong enough to do a lot. Okay, now on top of it, the position, okay, the position, say S, is 1/2 AT squared, okay? So the position is proportional to the time squared. So now A is proportional, of course, to force over mass if it was just a position. So A doesn't start with full A. A is climbing up slowly. And even if A started up with full A, because it's AT squared, the effect is like a square. At the beginning it's very little and then it goes faster and faster. So because of this effect, at the beginning it looks like it does nothing, and then it does like this, and then typically it maybe overshoots a bit or undershoots a bit and settles. And it settles, we'll talk about this too. This is a settling error. This can be like this or can be like this. This depends, of course, on the servo design. If it's critically damped, if it's underdamped, and it's not always that this is better or this is better. Sometimes it depends on the servo. For example, if you have a servo which has to deal with a lot of stiction and friction, maybe it's better to use this curve, because if it went over and a bit back, for sure it reached the target. See, if you did this, you never know, maybe it didn't have enough force to push to the target. So which response you choose has a lot to do with the use of the servo. Another example, if you do something in an oven, and it's temperature controlled, and you do something very critical in the oven, you certainly don't want an overshoot, because it can overheat. You rather wait a bit longer and do this. So the exact response depends on the application. Now it comes to here. Now you come to here, you tell the servo to go back. Same thing. It's a bit of delay, it does nothing. And then here it can do something slightly different, because depending on the mechanics and characteristics of the servo, just because it has an overshoot here, it doesn't mean to have an overshoot here. It could be different here. Okay, so this thing is called the steady state error. Okay? That's, by the way, in a PID controller, that's what the I is for, the integrator, right? Because that integrates it and tries to minimize it. Now, this is, okay. Now, when people say about the rise time of a servo, okay, so there is different definitions, but the most common definition when you specify rise time of an electrical pulse, of a servo, of an actuator, the typical definition is from 10% to 90%. So this is 10%, this is 90%, and this is TR, and the same for T4. That's the same as it's specified in electrical signals. Just to make it clearer, I'll make the response line heavy. So this is the response line. Okay, and the thin line is a command. Okay, so this is a command, and this is the output. Okay, now the reason why rise time is defined 10 to 90 and not 0 to full is because sometimes you don't see clearly what's happening here. If this is rounded and this is overshoot or undershoot, if you define rise time of the system by when it reaches 100%, some systems never reach 100%. Say they oscillate, so it's hard to define. It's easier to define. At 10% it's already clear what's happening, at 90% it's clear what's happening. Okay? So this is a typical servo response. Now, one big area of confusion is when people do calculations. Let's say you have a simple order system which behaves like an RC. Okay, first order single pole system. So when people do some calculations, they say, just a second, we learned at school that the time constant of this equals to RC, okay? And then if they draw it and they compare it to the rise time, they get a different value. Because if you draw this, okay, you draw this like this, okay, and you measure the 10 to 90, you get a different value than RC. Okay, and I think the answer should be clear just from the drawing. So why is the RC time constant of this different than the rise time?
That measures to a different value.
Exactly right. Because RC measures to 1 minus 1 over E, right? The definition of a time constant in an electrical circuit is a different definition than rise time. Because the RC of a circuit is the time it takes it to go from here to here, which at this point it's 1 minus 1 over E. Okay? Whatever it is, 63%, is it? I can't remember, but 67% or 63%, but basically it's 2/3. So the time constant is the time it takes something to go from 0 to about 2/3. That's the easiest to remember. Okay, and that's different than the definition of rise time. Okay, roughly speaking, the rise time is about 2 time constants. Very roughly speaking. Okay, so now let's go back to the original question. When you want to design a system, usually that's the spec given to you. Okay, you want the system to follow the command within a given time. Usually, the spec is usually given as the time to be within X%. So the way people specify it, they say, I don't care about this, I want the thing to settle from here I want it to come to within some error band. This is error band. So I want it to come within Z, which is a little bit more than the rise time, because it includes this time and maybe it includes a little bit of settling. Okay, and this in general is called the response time of a servo. So these definitions are not cast in stone, because you can define to any way you want what is the response time, depending what you want the servo to do. If the servo is not critical, if it has to be within 10%, your response time will be up to this point. If the servo is a servo to 0.1%, your response time will be up to this point, because it's still settling. So the response time is a vague term depending on your need of the servo. The rise time is a more clearer defined term. Okay, so let's say you're given this spec. This is the spec of the servo, and now what you really want to know to design the servo is two very practical things. You want to know the bandwidth, because the bandwidth determines the amplifiers, the filters, the motors, okay? And the other thing you want to know is the power, because if you select actuators, so basically, and accuracy, of course, you always want to know accuracy. So basically, when you translate this, when this is a spec given to you and you want to design a system, you say, okay, I understood what the system has to do, but how do I translate it to some practical things? I want to buy an amplifier, I want to know the bandwidth, I want to buy an actuator, I want to know the bandwidth and the power, and I want to put a sensor on it or some other thing, I want to know the accuracy. Accuracy is easy, because usually they tell you the error has to be, the total error has to be no more than X%, so the sensor has to be at least as accurate as X%, usually many times more. Now, one aside, most servos today are digital. So one common error what people make is, let's say that this has to be within 1%. You want a servo, for an example, that error would be 1%. So this is a spec. It's 1%, and you have to select a digital system. So one of the decisions in a digital system is how many bits of accuracy does the system need. For example, you have to buy A to D's processors. So do you need 6-bit, 7-bit, 8-bit? How many bits of precision do you need? Okay? So that's also a common error of inexperienced designers, because they say 1% is 1 part in 100. So that's total error, not plus minus. Total error band 1%. So inexperienced designers say, okay, 1% is 1 part in 100. So how many bits do I need to have an accuracy of 1 part in 100? 7. 7 is 128, right? 8 bits is 1 over 256, 7 128. Now 6 is a bit too low, 64. So typically you say, okay, if I put a 7-bit system, I'm plenty, because I can position myself in increments of 0.8%, 1 over 128, okay? But it turns out it's not true. It turns out you need at least 8 bits to achieve that. And the reason is because think of how a servo works. It always hunts around the target. And when you have a digital servo, if this is a target, the digital servo will hunt around it. It will go like this. And actually, most of the time, because of delays in the servo loop and so on, it's very common for actually to have like 2-bit errors. So 1 bit. So when you look at an output of a digital servo, at the best case, it will be plus minus 1 bit, because it has to hunt. And because you can't fall exactly in the middle of a bit. Say when you are between 2 bits, it will hunt, and it will hunt plus minus. But actually, most of the time, it actually hunts 2 bits. Because of delays and things like that. So even if it hunted 1 bit, and this is 1 over 128 of full amplitude, already the peak-to-peak error will be 1 over 64 of the full amplitude, which is 1.6%. Okay? So for sure you need 8 bits, because in 8 bits, this is 1 over 256, okay? And say 0.4%, this is 0.4%, so the peak-to-peak error will be 0.8%. But in reality, it will do this many times. So if you absolutely really need a servo to hold it total error to 1%, probably 8 bits are very marginal. You would go with a 10-bit system or 9-bit system. 9 doesn't exist. Most of these A to Ds and systems, they go 8-bit, 10-bit, 12-bit, 14-bit, 16-bit. Okay, so it's kind of not a standard number, a 9-bit A to D or system. Okay, but that's only when you deal with digital. So let's go back here. Let's deal with the fundamentals. This is what it has to do. Now, how do you translate this into this and this? Accuracy is quite clear. So the first question is, if a system has a spec of TR, you are given the TR, what is the bandwidth? Say, somebody tells you, system has to respond with a TR of 1 millisecond. What is the bandwidth of the system? Okay, that's something you should have run into in one of your courses somewhere, or if you ever build a servo. By the way, this conversion of bandwidth to TR, that has nothing to do with servo. Even if you do any circuit design, when you do a pulse circuit, any circuit design has the same question. You want it to respond, or a lot of times it's the other way. You have a certain bandwidth and you want to know what will the pulse look like. You have a filter with a certain bandwidth, you're sending a pulse through it. You want to know the rise time that the filter will limit you to. So the question shows up a lot in both directions. So what's the relationship between rise time and bandwidth? So anyway, to my surprise, I found out students don't know that most of the time. So yes, please.
Isn't the time constant 1 over the bandwidth?
Okay, so that's not correct. So that's what I don't know why, but I ask these questions every year, and I never found a student who knew the answer, because that's actually the most basic thing in electrical engineering, the relationship between rise time and bandwidth. Okay, so the answer is that most people say is the bandwidth is just 1 over the rise time. Okay, but it's not true, because you can see it's not true just from very simple drawing. So if you have a sine wave, let's say you have a sine wave, so this is, okay, so this thing is 1 over bandwidth, right? Because so many cycles per second, this is 1 over the bandwidth, the length of the cycle. But the rise time it does is faster than that, because so you can see this is one rise time, and this are another rise time. In other words, you can redraw the sine wave. You can redraw the sine wave to be above 0. Okay? And you can see that in one cycle, all what I did is I shifted it above 0. This is the center line of the sine wave. Okay? So you can see, without any math, just intuitively, that one cycle contains a bandwidth about 3 times. Sorry, one cycle contains a rise time about 3 times. So this is more or less a rise time, this is more or less a rise time, this is more or less a rise time. So a very crude way of looking at it, saying, if you take the sine wave, which is 1 over bandwidth, okay, the t is the length of the cycle is 1 over bandwidth, that's clear. Now you shift it above 0. Now you take the whole sine wave and just shift it above 0, okay. So basically you pick from this point, let's say, to this point, okay. Okay, so let's see if I did it right. Yeah, I mean this is like this actually, like this. But if you shift above 0, you can see, very roughly speaking, you know, this actually contains, and then you have to, you can have to go up to here. Sorry, that's not accurate, because if I take the sine wave and shift it above 0, okay. So if this is, so let's say I can go from here to here. I can only go up to here. This is a sine wave above 0. Okay. So you can see it contains at least twice the rise time, and actually more. So that's just to show you that the rise time is much faster than 1 over bandwidth. So it turns out, if you calculate it more accurately, you find out that roughly TR is roughly equal 0.35 over bandwidth. Now this, okay, this is derived, it's exactly this in a simple system. A simple system meaning a single pole system, the systems which do this, 6 dB per octave, so flat, and this will be 6 dB per octave. But it turns out, if you plot the response of a first order system, a second order system, and so on, the response times are not very different. So if I plot here the responses of different systems, so this will be the, let's say I plot the pulse response. So if I have an RC system, this is a command, the pulse response will look like this. If I have a second order system, maybe it will do like this. But in general, it's a very rough rule of thumb. Remember, that's not a mathematical proof, that's just a rule of thumb. So it's a general guideline or rule of thumb. Remember this, that the ratio between bandwidth and rise time is this. Okay, so yes?
Is that in hertz for bandwidth?
Pardon?
Is that in hertz for bandwidth?
Yes, that's exactly, and so this is, if this is in seconds, this is in hertz, if this is in, in milliseconds, this is in kilohertz, and so on. But it's the same unit. This is say seconds, and this is hertz, not omega, in hertz. Okay, so again, microsecond to megahertz, the same. Okay, so when you're given this, the way you make these decisions, what system to build, you say, okay, let's say this is given to you, and this has to be 1 millisecond. So let's pick an example here. If we were given a spec TR equals 1 millisecond, okay, then they say the bandwidth we need, okay, is 0.35 times 1 over 1 milliseconds times 1000, so it's 350 hertz. Okay, is that clear to everybody how I arrived at the bandwidth? I just used this formula, I just reversed it. A bandwidth is 0.35 divided by TR. Okay? And TR is divided by a millisecond is like multiplying by 1000. Okay? Good. So anyway, as I said, somehow when you learn control systems and you learn all these formulas, somehow for many students it's hard to make a connection between this and reality, like how do you convert this to bandwidth. So now you know. Good. Okay. Now one way to derive it, if you want to derive it yourself, all what you do is you know that for this system the bandwidth is defined as 1 over 2 pi RC, right? Because the 3 dB point, the 3 dB point of a simple system can be calculated, so you know the bandwidth. Now you know the formula for this, so you can calculate the rise time, so you can derive it from that by comparing the rise time to the 3 dB point of the system, and then you get this number. But what is interesting is that this number works not just for a simple RC, it's a very good guideline for all servo systems. Good. I also want to remind you this issue we dwelled a long time over of choice of filters for servo systems. That's a very important thing, because in every servo system you need some filter, and I explained, and I hope you remember, that a filter which looks great on paper like this, if this is F and this is A, could be actually very bad for a servo system. Just to see if you really remember, can somebody remind us why this could be very bad for a servo system? We spent a whole week on that.
You have a sync function?
Pardon?
You have a sync function?
And what's wrong with that?
Ringing?
Okay, so there's two things bad with that, because there is a relationship between the phase and the amplitude plot on any network. So if you have a simple network like this, the phase plot looks like this. Okay, this is phase and this is amplitude. So it goes up to 90 degrees phase shift. Now if you have a very steep amplitude plot, the phase plot is very complex and goes up to a much bigger phase shift. So since a servo is very sensitive to delays, it's very sensitive to phase shifts. So if you want to put a better filter, the first penalty is it can have very big and complex phase shifts, and the second penalty, it also has ringing, because if you send a pulse or a filter like this, it will come out ringing like crazy. And I even explained to you that if you send a pulse through a filter which looks like this. This is filter. Okay, it will come out ringing like this, and I ask the question, how can it start ringing before the pulse started? How does it know to start ringing before the pulse started? Right, if you take a scope and you send a pulse through such a filter, a steep filter, or a filter like this even, okay, it will come out looking like this. It will start ringing before the main pulse. So it looks like it could see the future. It could see a pulse coming. So how can it be that it starts ringing before the pulse? And we spend an hour on that too. Okay. Yes?
The whole thing's delayed?
Pardon?
The whole thing's delayed?
If correct, very good. Because actually, if you line them up in time, the input pulse looks like this, and the output pulse starts much later, because the filter has a delay. So, of course, it doesn't see the future. It starts ringing much after this pulse. And the more stages you have in the filter, the more delay you have. But the more delay you have, the worse it is for a servo system. So the filters which are very sharp, have perfect forms in the frequency domain, usually have much delay built in and much phase shift built in order to achieve this thing. And the reason you know that is the steeper the slope is, the more poles you have in the filter, because each pole gives you 6 dB per octave. So if you want 100 dB per octave, you need many, many poles, right? And many phase shifts, many delays. So I just want to remind you this chapter, because that's critical to design a system. Because the next decision, after you decide on this, you have to start thinking about which filters to put in. And what is the reason, let's see if you remember that, what is the reason why you need filters at all? Because if you say, I don't care if noise gets through, the actuator cannot respond to the noise. Right? The noise is high frequency, my actuator is very slow, why do I need a filter at all? So there's two reasons, which again we spend a week on those two reasons. So, why does a servo system need a filter at all?
Aliasing.
Yes, pardon? Aliasing, very good. How come only you remembered? So there's two reasons. One reason, most servo systems are digital today. You're going into an A to D converter. If you don't put a filter, there will be aliasing. And I don't want to start this whole lecture again what aliasing is. But okay? But there is a second reason too. So if it's a digital system, it has to have a filter. Otherwise, some frequencies will get created which didn't exist. And these frequencies can be very low frequencies that the actuator will respond to. That's called aliasing. But there is a second reason why you can't just allow unrestricted bandwidths to get into the amplifier. There's actually two more reasons. So if this is my signal, I'm just detouring from the subject because I'm a bit worried that you didn't seem to remember this basic thing about filtering. So if this is a signal and it's sitting on some big noise sitting on it, so the actuator can only respond to the base signal. But in spite of it, I have to filter out this noise even if the actuator cannot respond to it. Yes?
When you get positive feedback, you transmit the signal.
But the whole thing rolls it off. Like it doesn't go through the system. If you have an amplifier and you feed in this, the system cannot respond to it. After the actuator or even after the amplifier, you will only get this. So the system cannot, and this feeds back. So let's say if you don't have this consideration. But that's a consideration too, because actually you are right, because most amplifiers have more bandwidth than they need, but it can start oscillation even if you don't put in noise. If an amplifier has more bandwidth than you need, even without the noise, positive feedback can develop. Positive feedback doesn't need the noise to trigger it, right? Okay, but that's so you could say that you answered a different question. Why don't you allow too much bandwidth in the amplifier? Because of positive feedback. That's correct. But why do you want to get rid of all this noise even if the system cannot respond to it? So reason number one, aliasing. Okay, if it goes to a digital system. But even if it doesn't go to a digital system, there is two important reasons why you want a filter. You don't want this noise to get into the system. Yes.
Because a signal with a new frequency will be
Pardon?
signal with a new frequency will be generated.
Okay, so the answer is a new frequency can be generated from these two frequencies. And how can a new frequency be generated?
Because of nonlinear.
Very good. Because I went over it that in a nonlinear system, if you put in frequencies f1 and f2 at the output, you can get the sum and difference. Actually, you can get, if you put in f1 and f2 in a nonlinear system, you can get nf1 plus minus mf2, where n and m are integers. Okay? So I hope you remember that, because I showed you why. I even went through a proof with taking quadratic system, putting in a sine omega 1, sine omega 2, and coming out, we also got sine omega 1 plus omega 2 and omega 1 minus omega 2. I went through the whole mess of one example. Okay? So we have two reasons now for filtering, aliasing and what's called intermodulation, generating new frequencies, and the difference could be a low frequency, which will go through the amplifier. But there is a third reason. A third reason is practical, it has nothing to do with theory. Yes?
If you limit the bandwidth, can you get better gain at the regions you want?
Yes, but I'm saying, my question is, you are right, but I'm saying something different here. I'm saying even if the amplifier overall has limited bandwidth, I don't want to feed into it a high frequency. So the one is aliasing if it's a digital front end, one is intermodulation, but there is another reason why I don't want to feed into it a high frequency. Yes?
You don't want noise?
Yes, because the amplifier is made of stages typically, and maybe the first stages will be able to amplify the high frequency and generate a lot of noise. Because the higher the frequency, the less you want to amplify it, because it radiates like electromagnetic waves, like noise. So let's say your signal is 1 kilohertz, but there is a 1 megahertz sitting on top of it, say from some radio broadcast. That's very common. Every signal you look at, you can see about 1 megahertz sitting on it, because that's the AM bands. And then you can also see like 100 megahertz sitting on it. And if you have a good enough scope, you can see there's actually 1 gigahertz sitting on every signal. And that's from? Where is the 1 gigahertz from? From you guys, smartphones. you are reading this part, right? So if you have if you have a fast enough scope, you will see that on any low-level signal in the lab, there is this, and there is something faster, and there is something super fast, which you need a very good scope to see. And typically there is a 1 megahertz sitting on it, 100 megahertz, which is FM and television, and 1 gigahertz, which is smartphones. And today, probably there's a lot more of the 1 gigahertz than before. Remember, even if you don't use your cell phone, it still transmits and receives 1 gigahertz in order to know which tower to connect to. So cell phone is always transmitting, right? Because it has to be synchronized with the towers, but it's transmitting periodically, and it's, from time to time. But if you have a million cell phones, there's always, even if you don't use them, they transmit. Okay. So you need a filter not to allow all these frequencies to get even into the beginning of the amplifier, because they'll be amplified, cause more trouble. So now back to this. So now we know what bandwidth the system needs. We know what filter to put, and it's never this. It's always like a nice, gentle filter. Either a simple RC or something which is called a raised cosine. It's a very popular filter in telecom. So raised cosine is like if you take the cosine waveform, it's a first part of the cosine, but it's always a gentle filter. It's never a sharp cutter filter. Sometimes you go to a 4-pole, 2-pole or something a bit steeper like this. Okay, so this range is okay, this is okay, this is okay, and this is no. Okay, good. So let's continue. So, does everybody understand now, if you're given a spec of a servo system, how do you convert the spec to bandwidth requirement, bandwidth and filter requirement? Good. Okay. Now, I also spent time explaining how do you calculate the cutoff of the filter. Like, if, say, a filter has 2 points, a 3 dB point, and say a point where it transmits X%, 1% or whatever. Because the filter itself, in the frequency domain, is defined a little bit similar as the way this is defined in the time domain. Like you say, okay, it starts dropping from here and it drops to minus so many dB here. So how do I know, how do I calculate these points of the filter? So the most important point is here. Let's say I want the filter to cut off at a certain frequency to a certain amount. So does somebody remember how do I know at what frequency the filter should cut and to what amount? In order to specify the filter. Because the bandwidth of the filter is measured here. This is the bandwidth of the filter. The bandwidth of the filter, it's usually measured to 3 dB point. Okay, so I can easily calculate the bandwidth of the filter. It has to come out a bit more than this. But how do I calculate the cutoff of the filter at the bottom? So can somebody remind us? Let's talk about digital system. Let's talk about the same system we drew here. It's an 8-bit. It's an 8-bit system to give us 1%. So let's go back to this example. So I want to know how to calculate this point of the filter. Yes, please.
The accuracy of the least significant bit.
And this, yeah, so this has to be less than the least significant bit, but at what frequency? Because every filter eventually will go down to a least significant bit, but the question is where? So the two coordinates of this important point, it has to be less than a least significant bit at what frequency? Yes? Oh no. So, okay. Okay. Yeah, very good, good. So what you want to do is, at the sampling frequency, it has to be small enough that this will cause no aliasing, no error. Okay? So basically, and actually it should be at half the sampling frequency, okay? Because in order, from sampling theory, every signal should be sampled at twice the highest frequency. So actually, if you don't want to introduce any aliasing more than 1 bit, it should be this actually at half the sampling frequency. Okay? But basically, the thing which determines the lower part of the graph is you can't have like a 2/3 or 3/4 sampling frequency. You can have nothing. Right? Because at the sampling frequency, if you have a sine wave of 1 kilohertz and you sample it at 1 kilohertz, you get just noise, just garbage. It's all aliased. Right? So in order not to have aliasing, the signal should be less than half the sampling frequency. We went through this. So if you don't want to introduce even the one least significant bit of aliasing, then this actually should be half the sampling frequency. This is F and this is half F sampling. Okay, so now to summarize all that, so when you come to choose a filter for a servo system, okay, if this is F sampling for a digital system, and this is the highest frequency I can use in this system, which is 0.5 of F sampling, okay, so my filter should be like this. It should be as flat as possible, be nicely rounded, but whatever it does, it should be not more than 1 LSB at this point, because anything above there will be aliased. Okay? And so any one of those filters will be acceptable, and then there is trade-off. The trade-off is basically loss of speed or information. If I take a filter like this, it's basically meaning I'm slowing the system down, because I can't move at this frequency at full speed. But this is very good for phase and so on. So this is a trade-off in the servo design. Okay, I have to tell you guys that I'm a bit worried about you, because this stuff, this is the basics we went over just a month ago or 2 months ago, and you don't seem to remember it. So I want to tell you seriously that if you got the exam today, most of you would fail. So just be serious. Okay, you'll see on the trial exam, but if I gave you the exam today, you know, and there will be questions like that in the exam, you'll all fail. So you have to do some serious work before the exam. Okay, good. Because that's a legitimate question, like on the exam, you know, to calculate the filter bandwidth and crossover points and so on. Good. So, okay, so this is how you calculate the bandwidth, how you calculate the filter. How do you calculate the power you need? So power is easier to calculate because it's tied more to classical mechanical engineering. So let's say that this is a performance I want. I'm given the rise time, which means I'm given the bandwidth, and I'm giving the force. Let's say the servo has to act. Let's say I have an actuator. It's pushing some mass. Okay, and there is also some friction. There's also some friction force. Okay, let's say there is some pot here. There is some friction. Okay. And this is the response I want, and I want to know how much power. And the reason I need to know how much power, I need to know how big a motor or how big an actuator I need. Okay? So how do I calculate how much power do I need? So I know already the bandwidth, and I know F. I mean, depends if it's a constant force. Let's make it simple for now. Let's say there's a constant force. It has to oppose and a mass m, and I want to know how much power it needs. So how do I calculate that? That's a pure mechanical engineering question. This has nothing to do with servo. You have to move a mass against the force F. There's some friction maybe. How much power does it take? Yeah. So. Well, you know, you should know because you learned it. Yeah.
1/2 mv squared.
Pardon?
1/2 mv squared.
This 1/2 mv squared is only part of the power. That's all. No. Okay, but it's a good start. Okay, 1/2 mv squared doesn't take into account the force which opposes you, or the friction. It only takes into account the inertia. Okay, so the answer is this. The best way to calculate the power is you say what is the work done in one cycle, okay, and then times the number of cycles per second. That is the total energy per second, and energy per second is power. Okay, so you say let's analyze the full amplitude sinusoidal case. Let's say this servo has to move full amplitude. We know the bandwidth. In the example we took, the bandwidth was 350 hertz. A cycle here, okay, the rise time was a millisecond, but the total number of cycles per second was not 1,000, but only 350. So this servo, the rise time was a millisecond, but actually the total cycles per second it can do is 350. So if you can calculate the energy dissipated in one cycle, or needed to do one cycle, we can multiply with 350, we get the power. So the easiest way, if it's a complex question about power, the easiest way is get to it through the energy. I showed you the same approach when we derived forces. When we did the analysis, what is the force of the actuator, I also showed you how to derive it from energy. Right? In a moving iron actuator, we derived the force from the energy. So in most complex problems, it's easiest to start from the energy and derive the force, the power, everything from the energy. So if I want to move it, if I want to move this one cycle, so let's say I have a certain amplitude. The amplitude is A, okay? So I can calculate its sinusoidal. So it is, let's call this A to make it simpler. Just let's call half amplitude A. So the position will be A sine omega t, okay? Now from this I can take the force, the acceleration force, okay, will be the second derivative. Okay, so the velocity, so this is position, then I have the velocity. Okay, so omega a, so the maximum velocity is omega a, and the maximum acceleration, okay, is going to be omega squared a. Okay, and if I multiply this by the mass, I'm getting the maximum force. Or another way of doing it, if I have the maximum velocity, I can say, okay, the stored energy, if I take it from zero velocity to maximum velocity, I'm storing an energy of 1/2 mv squared. So per cycle, this is a part wasted on inertia. Now, of course, there is a fine argument here, because this energy is recoverable. So if I have a mass and a spring, I say, okay, but all this is recoverable. But this ties to the question in a servo, does it have regenerative braking or not? Since most simple servos don't have regenerative braking, to us, to the servo, this energy is not recoverable. You have to accelerate the mass all the way, and you can't count on it that it's coming back, like with a spring, right? Yes?
Even if it wasn't recoverable, don't you still need the same power to get to that point?
Yes, but if it's recoverable, you're saying that when you brake it, you know, when you move a mass in a servo, the first part you accelerate and the second part you brake, right? Now think of it, if you accelerate and brake, if it's recoverable, the braking energy is equal to the accelerating energy. So then it should need no energy. Because at some point, for every acceleration, there has to come an equal braking. Otherwise, it will go away forever, right? So if you have a mass, it doesn't matter if it's not sine wave. I have a mass and I move it fast, and I move it slow. But eventually, any acceleration I put into it is stored as kinetic energy. Eventually, this kinetic energy has to come back out, because I have to brake it, because it's constrained. The total position is constrained between two points. So it means every bit of acceleration I put in, which became kinetic energy, is still there, and I can get it back out, right? It doesn't have to be a sine wave. So if I have think of an electric car which has no losses. So every hill it climbs, that energy is recoverable going downhill. So because of that, in a big system, when you have regenerative braking, you can say, I don't need to calculate that. I don't need to calculate this at all. Because if it has perfect dynamic braking, all this energy eventually comes back by very clever dynamic braking. Regenerative, not just dynamic. I mentioned to you the difference between dynamic and regenerative. Dynamic is just you apply some power to the motor to stop it. Regenerative, you actually take the energy back from the actuator. So strangely enough, all the inertial forces which cause power is fully recoverable. Now, in reality, it's 90% recoverable, because when you make the actuator into a generator, the efficiency is not 100%, say 90.
To initially put the initial energy in the system, don't you need the power that you calculate from the beginning?
Yeah, but but that's just when you start. When you talk about, okay, you need initially the power to accelerate, but in terms of overall, let's talk about things like heat dissipation on the amplifier and things like this. So you do need the peak power to be able to move, but the total power in terms of heating losses, if it's recoverable, is much less. But we are not going to go into that, because for most small servos, things are not regenerative. So not just the peak power, but even the average power is there. You have to supply the power, you're not recovering anything. The only reason I mentioned it, that if you design an enormous servo to, I don't know what, to move bridges or something, then it becomes a factor. Then you say, I'll design it in a way that I can recover a lot of the energy, because we're talking about big energy. To give you another example, you asked me about don't you need the initial power to start moving it? There is ways around that too. So if I have a battery in the system, then this battery always has the last energy stored into it. So when I turn on the system, I have in the battery the energy from the last recovery. So even theoretically, you know, if the system has some way to store a bit of energy, even when you start it up, it uses that energy. And again, think of an electric car. If you climbed up the hill, and you stop the car, you have the kinetic energy of that hill stored in the car, right? Or if you went down the hill, you have this energy stored in the battery. So it's even recoverable when you start it up, because if you have a storage device, which can... But let's not get into all that, because that's getting too complicated. So let's make it simple. You have some energy, which is 1/2 mv squared, plus you have some irrecoverable losses, and the irrecoverable losses is simply you have to oppose a force F for a distance A, or if you go, so if you want, so you have to, so basically the losses here is distance times force, because this is work, because work is force times distance, right? Work is F times delta x. So if you have a force acting against you when you have to move delta x, you have lost energy. So that's a very, very rough calculation. I'm not even getting into the exact calculation of the distance. I'm just saying in general you have energy here which is inertial, which theoretically is recoverable, but you never do it in small servos. And then you have work which is not recoverable, for example friction or opposing. If you have a constant force, theoretically that's recoverable. Because a constant, you think of it, if you go against a constant force, you push it and you put in energy, and then the force pushes you back and you get the energy back. Say gravity. Let's say you have a servo which controls an elevator. It lifts it against gravity with a force F. In theory it's all recoverable. But if you don't have regenerative systems, even that is not recoverable. So for small servos, like a machine tool, a disk drive, no energy is recovered. So per cycle, you have the kinetic energy, plus you have the dissipation, you have F times delta x, and all this is times as a frequency, times the frequency, because this is per cycle. So it's a very crude way to look at it, but that's good enough, because you are not going to choose a motor just marginally. You always choose an actuator which has some safety margin. So this gives you an idea how much energy the system needs. So now you know the bandwidth, you know roughly the power you need. Now another way to approach it is through force, not through energy, because you know in this case you can approach it through force because you have a mass m. You know the maximum acceleration here is omega squared a, so the total force is omega squared a times m plus f. So if you want to specify the actuator by force, not by power consumption or power output, it's even simpler. This is a force to accelerate the mass. It's a peak, it's a point of maximum acceleration, plus a constant force. And the constant force could be, for example, some mu n, some friction force, could be any other force. So if the actuator is limited by force, if that's a weakness, it's easier to do it this way. Calculate the peak force, compare it to the data sheet of the actuator. If you're more worried about energy, say motor getting too hot, then you should calculate the energy per cycle times the hertz. Now, the usual pitfall whenever you calculate heating of something is that people use the average instead of the RMS, and we went through it enough times that I don't think you need to be reminded. Because you have to know when to use the average, when to use the RMS, right? So unfortunately, say when you it depends what you're trying to find out, but the main thing is if you're worried about heat limit, like steady state limits, heat limits, you have to use RMS. So now, the more spiky the system is, the bigger the ratio between RMS and average is. So in other words, spiky means if the system just works like this, it operates very quickly and rests for a long time. Okay, so I gave you many examples like that, the RMS and average. Okay, what is the ratio between RMS and average on a sine wave? I mean, average is 0, but let's say if you rectify the sine wave, if you took the sine wave and rectified it, okay, you would have an average value, but you'll also have an RMS value. Okay, so in a sine wave, what's the ratio between RMS and average? How much? No, 1.11, because you can calculate the RMS is 1 over root 2, and the average is something like 0.6. It's something with 1 over 2 pi. It has to do something with pi, 2 over pi, I think. If you do integrate the sine wave, find the average, then the ratio between them is roughly 1.1. So for a sine wave. So in sine wave, it's not bad. If you rectify a sine wave, it's not bad. If you mistake the average for RMS, it's only 10% error. Okay, but if you're dealing with pulses, it's a very dangerous mistake to make. Okay, so this is like a general guideline. None of that is highly analytical. It's just common sense. Okay, it's just common sense how to estimate the bandwidth, how to estimate the power, the accuracy, and the important thing is about the number of bits, which is a common mistake, and heating. You go by RMS, and now you can specify the parts of the system. Okay, so is that whole discussion clear? Okay, so let's go through an example. Let's. So let's just take a random example. I have a robot which has to spray paint cars. It's a real life example. So you have a car. Okay. Now there is a robot arm. Let's make it even simpler. Let's say it's a Cartesian robot. So you have one track this way. Okay, and you have one track this way, and on this there is a spray gun mounted which sprays the car. Okay, and I have a servo system because I program this robot with the shape of the car, and it has to paint the car. Okay, so I have to specify the servo system components to do that. So let's say the car is 5 meters by 2 meters, could be any shape, okay, and let's say that each pass of the robot is 0.1 meter wide. So the way I paint the car, I have a circle of paint, and I just move it like this, okay. So and the time to paint this side of the car, let's say the time to paint is 10 seconds. So what I want to know is, for the system, which bandwidth do I need of the actuators? We can talk about accuracy, although here, let's say, accuracy is 1 centimeter. So I have to design the system. So what I want to know is which bandwidth do I need out of the actuators? If I have sensors, what kind of accuracy or what sensors do I need? And also I need to know which kind of filtering and which power, how much power does the actuator need. To make things simple, let's say that the payload here is 10 kilo. the payload includes the bar and the cables and everything which has to be moved around. So a total mass of 10 kilos to be moved around, 10 seconds to paint the car. This is dimensions. So, and I want to know bandwidth, power, choice of actuator, which actuator, and choice of sensor. Okay, so that's a typical question in approaching a servo system. Will also be a typical question on the exam. That's what the question looks like. Okay, so I mean, you can do all kinds of clever things, but to make it simple, let's say it's a simple raster scan. I just go back and forth. So, because I don't know which shape the car is, the car can be like this or like this. I have to cover a rectangle, basically. I can't do any tricks, take advantage of the fact that there's nothing here. Okay, so basically, so the first question is, how many lines, scan lines, do I need to cover this? So I have an area which is 2 meters by 5 meters. So let's start with a simpler question. Is it better to do the raster this way, or is it better to do the raster this way? Okay, what do you think?
I think going over.
Yeah, why and why?
Less direction changes.
Exactly, because you lose sometimes the direction changes, you lose accuracy, so for sure it's better to do the raster in the long direction. Good. So if this is 2 meters, I have to cover 10 centimeters, okay? So I need at least 20 scans, okay? If you are a good student, you will put a note that it's better to use 25 scans, because if you think of a spray gun, it's probably a bit like this, right? So probably you want to have some overlap just to get nice painting. So if you really were designing it, not just for the exam, you'd have said the minimum is 20, but it's very bad to leave a gap between scans, so let's make it 25. Okay, so you have 25 scan lines, so 25 lines. Okay, each line is 5 meters long. Okay, so from this we can calculate. So now we converted this whole problem into a different problem. You go like this. Okay, you go like this, 5 meters. You have 25 lines. Okay, so what bandwidth does the system need? So here bandwidth is actually a bit harder to assess, because as long as you go straight, you don't need any bandwidth, right? Because once you moved up to speed, this whole 5 meters, you go at constant speed, there is no bandwidth required. But the bandwidth is mainly required to reverse direction. So this question is actually a bit misleading, because it's a judgment. It's a judgment call. I can go very, very fast here and then take my time to reverse. Or I can go slow here and reverse very fast. Okay? So that's the judgment element. So if you get such questions, any answer would be accepted as correct. Because if it's a judgment call, I mean, you can say, okay, let's optimize it. What is the total minimum time to paint? But you don't have to get into this level. So if you're given a question like this, you just make an arbitrary judgment saying that let's calculate the time per line and then arbitrarily decide how much time will be allotted for reversal. So what will be the time per line? So I have to all together I have 25 lines and I have 10 seconds. Okay? So the time per line would be 0.4 seconds. I take 10 seconds, divide by 25 lines, so I'm getting 0.4 seconds per line. Just, okay? So now I arbitrarily decide that this will be, say, 0.3 seconds, and the reversal will be 0.1 second. But any other value would be accepted. Now remember, you don't have to add both reversals, because basically each line includes one reversal. Now the second line is a line and includes one reversal, right? So you don't have to count the reversal twice. Okay, so arbitrarily I assign 0.3 seconds to the line and 0.1 second to the reversal. Okay? And now I can start calculating bandwidths and forces and so on. Okay, so is this clear so far? Good. So during the linear travel, if it's constant velocity, in theory there is no power needed, it's just friction to overcome friction. But constant velocity, and if this runs on some nice rollers, say it runs on some nice rollers, it slides. So this part is of no interest. It's just of interest if I use a motor, I have to check what speed the motor has to run. Because at the end I have to suggest an actuator. Since this is 5 meters, it's not reasonable to do some linear actuator 5 meters long, right? It's more reasonable to put a belt. And that gets into the other part of the question. In these questions, I always say suggest a mechanical configuration, which means you have to make a sketch. How would you actually build it? So then you have to think a little bit as a mechanical engineer, saying how would you build it. So a good way to build it, you take a timing belt. You take a timing belt, connect it here to a motor, and then you will attach the cross slide to the timing belt. And here you'll have the same. You'll take another timing belt with a motor. There's also a timing belt, and then on this thing you'll have the spray gun attached to the timing belt. And this way you can do it with rotary motors. You don't have to make actuators which can move 5 meters. Okay? I mean, you can argue that you can use a linear motor, but it's much more expensive. So again, here whatever you will say, as long as it makes sense, is acceptable. I mean, the right solution in a case like this is actually a timing belt. But if you will say, I want to make it pneumatic, I want to make a long air cylinder, that's fine. Or if you want to say, I want to make a special lead screw, as long as it's not crazy, it will be accepted as the correct answer. For example, a steel cable. What you can do here, you can take, instead of a timing belt, is a steel cable or a steel ribbon. That's acceptable. Okay? Okay, so now we can start estimating how much bandwidth I need, because what I need to do is I can estimate both the force and the bandwidth. The force is easy. I have to take a mass of 10 kilo. I have to bring it to a stop and reverse it in 0.1 second. The velocity here is known. The velocity here is known because it goes 5 meters in 0.3 seconds. Okay? So the velocity during the linear part, okay, is 5 meters in 0.3 seconds. Okay, so it's about 16 meters per second. By the way, in the exam as well, all calculations can be rounded. You don't need a calculator, because it says on the exam you only need to calculate to plus minus 20%. So don't bother with calculators. You just say roughly 16 meters per second. Okay, so now, now I can calculate the acceleration. Right, because you have the time. It's easiest to calculate on half the time, because 0.1 second is to do the whole reversal. So to stop and to accelerate, each one is 50 milliseconds. So you got 50 milliseconds to go from 16 meters per second to 0, and then you got another 50 milliseconds to go from 0 back to 16 meters per second. Okay? So from that, it's very easy to calculate the A, acceleration. You multiply by 10 kilo, you get the force. Okay? And you calculate, if there is no regenerative braking, you calculate the kinetic energy. At this point, you have 1/2 mv squared, which is 1/2 times 10 times 16 squared. Because at this point you're running at 16 meters per second. That's 256 times 5. It's about 1300. So at this point you have 1300 joule. Okay? So as energy is 1300 joule. Okay, so if you want to know the power, 25 times, so no, a line is 0.4 seconds, so 2.5 times a second, because you have 25 lines in 10 seconds. So 2.5 times a second, okay, you have to decelerate and absorb 1300 joules, and then you have accelerate and output 1300 joules, but we count it as the same. We don't have regenerative braking. So we basically say you have to output power of 1300, energy of 1300 joules twice, and 2.5 times a second. Okay? That's a very crude calculation. Okay? The reason why it's crude, because you can immediately, if you are a smart student, you immediately say, no, what a smart student would say, let's put some spring bumpers here. Okay? If I put a spring bumper here, I don't have to do anything. It just hits a spring, compress it, and re-accelerate. And I just have to add the friction. So the difference in the exam between A and A plus is, if you just calculate it right, you get an A, but if you sort of it that you can do something simple like a spring bumper, you get extra few points. Okay? Because that's kind of calls for it. It really calls for some good idea here, just not to waste 1300 joule at each end. Okay? Because this is in a way regenerative braking, right? But it's without all the complexity. Okay, good. So now you have most of what you want. You have the bandwidth. The bandwidth is derived from Z. Okay? Because you have a rise time. You have roughly a rise time and a fall time of 50 milliseconds. So the bandwidth is roughly 0.35 divided by 0.05, which is 50 milliseconds. Okay? So that's about 7 hertz. So the bandwidth is actually quite low. Okay? That's just to check when you pick a motor or an amplifier, just to get an idea what bandwidth you need. So let's say it's about 10 hertz bandwidth system. So when you put amplifiers in, filters in, it's in the order of 10 hertz system. There is actually a simple way to do regenerative braking. So the power you need is just maybe 20% of the energy. We said the energy here you have to dissipate 1300 joule and then input 1300 joule. But if you have some kind of a spring or a bumper, maybe you assume 20% of that would be enough. Because if it was frictionless, you would need 0. Because frictionless, the spring will absorb all the energy at the end of the travel and output it all back, come back to this velocity. So when you say how much energy do I need, you just make a guess. You say, well, it's not frictionless, it's not perfect. Maybe 10-20% of the stored energy is still wasted. And any number you pick, you get full credit, because I don't know myself. Nobody knows. Depends on the system, right? You just have to be reasonable. Not to say 0.01% and not to say 90%. Okay, so this is what I mean by system design. So now we know the bandwidth, the power, the maximum forces, the speed. Accuracy is not a big deal here. Because if accuracy, you need some kind of a sensor, because you need 1 centimeter. So this motor has to have some kind of a sensor, maybe a shaft encoder. Okay, and you have to run it closed loop. You have to run it through the shaft encoder to the motor, and here is a command. Here is a command. Because you can't just rely on an open loop motor. If it was a stepper, you wouldn't need the shaft encoder, but a stepper cannot provide such powers. So we're talking here about, even if at 10% of the energy, we're talking about hundreds of watts, right? Because without that, it was 2500 joule times 2.5, right? Was 6 kilowatt. Okay, but if I didn't make any mistake here, sounds a bit high, 6 kilowatt. But anyway, it was many watts. But even with regenerative braking, we're talking about hundreds of watts. So obviously it's not a stepper motor, which means we have to have some other motor, say induction motor, okay, and then it means we have to have an encoder. Could be a DC motor as well, but still means you have to have an encoder. So in terms of sensor, a regular encoder is good enough. one of the issues you always have to think of is, how do I know when I start where it is? Because when you start up, the motor starts running like crazy and may hit the end. So every good system design has to have some sensor. Either you put an absolute encoder, so I know where it is. In this case it's difficult because it's multi-term. Okay? Or you just put a sensor here. You put a sensor here and a sensor here. And that's how actually most systems work. They just have a micro switch here, because this sensor doesn't have to be that accurate. It just tells you it's end of travel. So when you turn on a machine like a CNC machine, it always goes to one end, hits the limit switch, and says calibrated. And then it measures with a non-absolute sensor. Okay? So this whole process, this is steps you take in a servo system design. This is not how to do the servo itself. Of course, you have to write code for the servo. That's a different problem. This is just, if you're given a spec, how do you convert it to parameters you look up in a data sheet? How do you convert it to bandwidth? How do you convert it to power, to force, to accuracy? Is that clear? Good. So we're going to do one more exercise like that on Tuesday, and that's it. Okay, thank you.